Silver team along with Robbie Peoples and Brent Griffith. And our experiment is a spray paint booth pressure control system. And I'm going to be presenting our findings on steady state operating curve and the step response observation. First, a little background. There's an engine assembly plant in Dunlap, Tennessee that has one of these spray paint booth system that is used to paint engine housings. The booths are pressurized by a variable speed blower. These here are solenoid valves or dampers that can either be open or closed. If they're open, pressure is allowed to get into all three booths. For instance, if this one's closed, it cuts off pressure to both these. If this damper right here is closed, it cuts off pressure to booth 3. For the purposes of our experiment, both dampers were closed, so whatever pressure comes into the system is only affecting booth 1. And then as the exhaust goes out, it's filtered per EPA standards and regulations. Speed of the blower is controlled by the user, so that's the manipulated variable. You're able to put in, it's measured in percent of the total motor power, so you can put it in as 100%, 0%, or anything in between. The output of the system is pressure to the booth, which is measured in centimeters of water. That's the control variable. So the objectives of our experiment were to create a steady-state operating curve, which can illustrate the relationship between motor, power input, and booth pressure output within the system, and also to observe the system's steady-state gain, dead time, and response time during a step function input. This is the kind of the procedure of how the system works. You got operator inputting power into the system. The LabVIEW control program is used in this experiment that is outputting to the equipment how much power should be going through, so how much the speed of the blower is what that controls, and what's coming back is the pressure in the booth, again in centimeters of water. So the operator inputs a desired input, experiment time, and for the second part of our experiment, a percent step up or a percent step down. And what comes back is a pressure level, the actual pressure in the booth. And then from there it goes into a Excel spreadsheet, or I guess some other kind of spreadsheet could be used too, but we used Excel. So that's where the data is sent, collected. So this is our data collection for the steady state portion of our experiment. The system was run at various power inputs. And this pressure versus time graph was created at each input. An average pressure is determined at each input. And so that's this section in here. Section over here doesn't matter, but once it reaches the steady state, we figured out an average pressure. So for this one, this is at, looks like 75% of the blower speed. And what we come up with for this one was 35.2 centimeters water with uncertainty of 2.6 centimeters. And all of our graphs look approximately like this. I mean, they're higher up or down based on the power input, but that's pretty good representation of what they look like as far as once the steady state is reached. This is our overall results for the steady state. We came up with this operation curve for these 3 ranges. This is the higher input, middle input, and lower power input. So this graph represents, you know, if you could use this graph if you knew kind of how much power or pressure you wanted to get out, you could use this graph to try to estimate how much of the blower speed you need to use. Of course, it doesn't go across the whole range, but it could at least be used for these 3 ranges. This is the second portion of our experiment. This is a step response. our system was run at specific power inputs, then either abruptly increased or decreased. We used 10% over the whole experiment, or this portion of it. Power input and pressure output were graphed versus time for each trial. And some of the things we were looking for was a steady state gain, dead time, and response time constant. So this is an example for one of our trials. This was a jump up from 60% power input to 70. So again, a 10% increase, which is represented by the delta M. And this is the actual pressure, and I guess that's like pink color, which is output in centimeters water. And an average was taken for the first part of the experiment and then after the step up. And the difference between those two, measured in centimeters water, is a delta C. So one of the things we were looking for here was the steady state gain, which is represented by K, which is equal to delta C over delta M. So for this one, and that of course is measured, the units for that is centimeters water over percent. So for this one, it comes out to 0.89. Also dead time, which is the time between when the step was initiated to when the system actually goes up in pressure. So for this graph, it looks something like right in between here is when you see that's when the step was made, and then right there is when we approximated that the pressure actually started to go up. So the time in between those is what's called the dead time. So for this particular graph, that was 0.14 seconds. And also the time constant, which to get that, we had to first calculate 63.2% of delta C. And wherever the sharpest part of this slope met that line, drew a straight line down, and the time between there and when the pressure started to go up was our time constant. And so for this particular graph, that's 0.09 seconds. So this is just one example. We ran about 18 or so of these. These are our overall results for the step response portion. This is the results of our steady state gain, or K. Tests were run for up steps and down steps at the lower, middle, and upper power ranges. And these are our results for this particular item. The values vary based more on region. So in other words, from lower to middle to upper, they vary, but not so much based on the direction of the step, which you can see is shown by this graph, in that each and lower up and lower down are about the same gain, same for middle, same for upper, but they do increase as you go up in power. Second thing we were looking for was dead time. Again, steps were run for up and down steps at all ranges. And these values vary based both on region and direction of the step. So the steps down had a longer dead time, or time for the pressure to actually go down, than for the steps up. And also, the higher the power, the longer the dead time as well, which is why these ones in the lower range are lower on this graph. And the third thing we were observing was the time constant, tau. Again, tests were run for up steps and down steps at each of the ranges. And these values for variance were pretty unpredictable. So from lower up and lower down, there's a huge discrepancy. And then you're kind of all over the map with these ones, and the uncertainty was higher for these. So there wasn't a whole lot of predictability to that particular measurement. In conclusion, we figured out that it takes about half a second to a second for the system to reach steady state once it's turned on. Steady state curve can help the user reach desired pressure within the given input ranges. But more work would have to be done in order to figure it out across the whole scope of it, which would be 0 to 100%. And the paint booth system's steady state gain, dead time, and response time